It's level. That's low.
Anyway, so good morning. Thank you for continue attending. So it's my pleasure to introduce my friend Kathleen Wilkie. She's going to give a talk now. So these talks are only going to be about 20 minutes. So just to leave some time for questions. Okay, thank you so much.
All right, thank you very much, everyone. So I'm going to talk about fractional versus ordinary differential equations in cancer modeling. But before I get that, it's not working. The button is not working. Before I get to that, yes, please call him because if I press enter, oh, I just tap. Okay. Okay, no, it's okay. Thank you. We figured it out. Before I get there, I just wanted to introduce myself in the context of Siv's timeline, because we are all here in honor of Siv. So I was an undergrad at Waterloo. And of course, at the, I'm not going to date myself too much, but at that time, he was really making waves in the department with all this really cool sounding math medicine stuff. And I saw some really awesome people before me in the audience today, Katrin and Karina, in particular, working on really cool stuff. And so I asked Siv and Dr. Tenti if I could work with them as an undergrad, and they told me no. So I had to go and do fluid mechanics. And then I came back and I did my master's, and then I approached him again and said, please, I really want to work with you. Can you take me for a PhD? And so he said yes. So finally, I got into the math medicine group and did my PhD with Siv. I thought it would be cool to pull up the lineage of, from the math genealogy project, but as you can see, he has no known students, even though we're all standing here and sitting here in the room. So I think maybe this is, they don't recognize Canada, or we need to actively change this. But none of us are apparently listed. Anyways, Siv's advisor was John Rolette. I'm not sure how you say it. And his dissertation was analytical and computational aspects of buoyancy-driven flows. So maybe doing the fluid mechanics, put me in the right area. Anyways, during my time there, Siv was very involved here at the Fields. He formed the Center for Math Medicine with, as already mentioned, Dr. Oza and Dr. Drake. And then they didn't have the previous history, but there was a lot of math oncology workshops that were run here. And in particular, formative for me was the first thematic program on math oncology that ran in 2008. And there was so many workshops, and the SMB meeting was organized here. And this was really formative for me. As a group of PhD students and master's students from Waterloo, we all got to come down. We lived in the dorms. We attended all these workshops and summer schools and the SMB meeting. And I remember one of them in particular actually came with a little bit of funding for us. So we all organized as grad students to stay 2 nights in the Royal York, which is this really fancy hotel down here. So that was fun for us at the time. I looked back at the SMB meeting, and I wanted to point this out because I thought it was interesting. The sessions each had about 1 cancer stream. This afternoon actually had 2 cancer streams, but each day pretty much had 1 cancer stream, whereas SMB this past summer had 3 every single time. So you can see how much the field has grown for mathematical medicine and mathematical oncology. So this is the pictures that I could find. Of course, nobody really had cell phones back then, but some of the funny players are in the audience here today. A big thank you to Jibin and Colin Phipps, and some of the friends and colleagues couldn't attend apparently. Yes, yeah, and actually at SMB in 2008 was the first time that I met both Natalia Komarova and Helen Byrne, although I probably didn't remember us because we were PhD students at the time. Anyways, so my thesis was on cerebrospinal fluid, pulsations, aging effects, and mathematical hydrocephalus, not at all on cancer. But what I thought would tie my talk today in with my time with Civ was the fact that in this thesis, which was done collaboration with Karina, we looked at fractional derivatives and fractional models of viscoelastic materials. So that leads us into fractional derivatives. And we're going to look particularly at fractional derivatives for tumor growth models. And the first one to talk a little bit about why. Why would we want to look at fractional derivatives? There is some evidence, you're introducing another parameter in your model. So there is the potential for more accurate models to be had. And they have been successfully applied to many applications, not just in my thesis, but to COVID modeling more recently, and lots of tumor models. If you Google it now, you'll find fractional derivatives and cancer models popping up all over the place. And there is a suggestion that it's not so far-fetched that experimental data suggests that the cells do behave like little viscoelastic bubbles. And that this viscoelastic response can sort of drive their cell behaviors. And so since fractional derivatives have been so successful in the field of sort of engineering and materials sciences, I guess it's sort of moving into math oncology as well. So there are many different definitions of the fractional derivative. We work mostly with the Caputo fractional derivative because it involves an initial condition, which then makes it suitable for application. So here's the definition of a fractional derivative. If you've not seen one before, it has this sort of fading memory through this convolution, and it captures heterogeneities, multi-scale fluctuations, and memory effects. The problem with working with fractional derivatives is that we need special numerical integration techniques to work with the derivative. So here's some examples of what's been done so far in math oncology. This paper by Bolton in 2015 proposed a fractional Gompertz model, and they fit it to this data set, which you can see is sparse. The solid line is the fractional model, and the dashed line is the regular ordinary derivative model. They claimed that this was a better fit. Here's another example from Valentim et al. In 2020. The top lines, these are first order derivative models, the standard exponential, logistic, Gompertz, etc. And at the bottom, they did fractional derivative models, and they said, again, the fit is improved. And arguably it is, but as we'll look at in this talk, is the improved fit worth the cost of the extra parameter? And I would argue no. The last example I pulled from the literature was Eric and Araz, and they did a three-phase model where it's like an ODE, SDE, and an FDE to model sort of before treatment, during treatment, and after treatment phases. So people are doing interesting things with fractional derivatives, but is it sort of benefiting clinical decision-making or moving towards being able to do better predictions for virtual trials, et cetera? That's the question that I'd like to look at. So we considered three standard models: exponential, logistic, and exponential linear. And then we considered their fractional counterparts by replacing the ordinary derivative with the fractional order derivative here. And then, because fractional derivatives are a bit annoying to work with, the right-hand side has to be a continuous function. Standard way of modeling radiotherapy in math oncology is an instantaneous sort of stop and restart your integration technique. So when you want to stimulate cell death after a fraction of radiation dose, you stop your integration, you reduce the population by its death fraction, and you restart the integration. You cannot do that with a fractional derivative, because as soon as you stop the integration, you're going to lose the memory, right? And then we want to continue the memory on. So we introduced a continuous way to describe the radiation effect. So we use the linear quadratic. Yeah. Yes. Yeah. Yeah. So we spread the death caused by, this is okay. We spread the death caused by the radiation out over a window. We called it the treatment window. And then we used an approximation here for the Heaviside function to turn the radiation on and off over the window. So in this, actually my student Nicole's thesis, we considered only small windows, looking to in the limit as the treatment window goes to 0, so that we could always compare with the standard, which is the impulsive model. But this is not necessary. You could let this treatment window go to 1 day and say that, radiation occurs now, but it might take 1 day for the full effect of the radiation to be enacted on the cells.
In other words, your approximate when epsilon goes to 0. Goes to 0,
Yeah, so this,
and then you can
yeah.
see delta function.
Yes, it's approaching so this is approaching like a step, right? And then when you put 2 together, we'll be approaching a delta function. Exactly, yes. So in the limit as the treatment window goes to 0, this approaches delta function. And so now we have the 6 models that we will compare: 3 ordinary derivative, 3 fractional derivative, where it's exponential, logistic, and exponential linear, with the sort of treatment window radiation effect on the end. And then we had some treatment data from a collaborator at the Moffitt Cancer Center, where there was 19 head and neck cancer patients that were treated on weekdays with 2 gray fractions. And so they were measured, I think, weekly. Nicole went through and figured out all the days that they could possibly have been treated from the data. And we made some assumptions that reduced the number of parameters a little bit, like the logistic carrying capacity is going to be taken to twice the initial volume, et cetera. And then that left with a few parameters. We assumed the radiosensitivity parameter to be beta to be proportional to alpha. So we only had to estimate alpha, the growth rate, and the lambda 0 and the lambda 1 for the exponential linear model. And this is an example. I'm not going to show you all the 19 patients, but this is an example of one that is sort of an average responder. So on the left side here, this is the blue stars are the patient data. And then you have the exponential, logistic, and exponential linear models fit to the data with the ODE models. And on the right here, you have the fractional derivative models, and they look almost identical. When we looked at the fitted parameters, which sort of will tell us, what the model is actually doing, you can see this, the left side again is the standard ODE model, and this is the FDE model on the right. Most of the dots, these are like for each model, exponential, linear at the bottom, sorry, exponential, logistic, exponential, linear. Most of the dots are in the same spot for each patient, but a few patients, when we are fitting the order of the fractional derivative, will change. Like patient 3 jumps out here, patient 2 jumps up here, and is fit with a lower order derivative. Most of these fractional derivative models are fitting with the order of the fractional derivative very close to 1 in actuality. The color is the order, yes, here. So if they're all magenta, then they're all 1. And there are only a few where the order differed from 1. Here we can see the sort of range of the parameter values that were fit to each model, whether it was ordinary or fractional. And you can see here on this plot that most of the fractional models were actually fitting with an order of 1. I'm going to show you the sensitivity when we allow for the fractional order to change. And this is now I'm forcing it to change. And you can see as the order decreases from 1 to 0.8, so look at the yellow, the mustard yellow color line, you can see that with each fraction that was delivered, there is a large drop, but then an incredibly rapid regrowth. And I argue, and I will argue again, that this is not physiologic. So this is sort of an artifact of the fractional derivative being less than 1, that we have this unphysiological regrowth happening. So in order to do a proper model selection study, we have to look at information criterion. So we use the Aka-Ike corrected Aka-Ike information criterion and the Bayesian information criterion as they're defined there on the slide. And then with those information criterions, you can do a whole bunch of different things if you want to. Nicole, my student, did a whole bunch because she got a little bit excited about it. You can calculate the information criterion. You can calculate these delta values, which is where you select the minimum off of it. Then you can rank them and tally them, which you did here. You can calculate weights, which you did here, and then the same for the Bayesian information criterion and the Bayesian tally. And basically, in weights, you want a high number, and everything else you want a low number to be the best model. And the best model turns out always to be the exponential model. It has the least number of parameters and with an order 1 derivative across all the sort of metrics that we looked at. So even though the FDE model could arguably increase the fit, the increase to the fit is not worth the cost of the extra parameter that you have. The kind of fun thing that came out of this was that we had created this way of continuously describing the effect of the radiation dose, which we looked at a little bit closer. And as we shrink the, as we shrink the treatment window TW down to as close to an impulse as we can get numerically, the fits are actually quite stable and the SSR is stable. So we are approaching the sort of stop-start method in the limit. And when we look at the time that we were taking in our, if you look at like ODE 4.5 here, we were fitting 100, we fit the same data set 100 times. And it took on average about 3 seconds to fit, whereas the impulse method took about 6 seconds. And if you used a heavy side function, then it was horrendous. It was like 875 seconds. So we have the time of the stop-start method by using a continuous description, which is, better suited to the type of optimization method we were using, I guess. So that has an advantage then if we want to look forward and do, larger model parameterization problems or virtual clinical trials. So in conclusion, fractional DE models can be used to capture heterogeneity and multi-scale effects in tumor growth, but should you do it? I mean, it's an interesting mathematical problem, but I'm not convinced yet that it provides added power to the predictiveness of the models. You have to also be a little bit careful because, as I showed you, you can get unrealistic regrowth in the model with the fractional derivatives. When we did a model selection analysis, we found that the simplest was, of course, the best, and that was the exponential growth model, which in this study had the same number of parameters as the logistic model because the carrying capacity was fixed. And then lastly, the death rate term, I would encourage you if you want to study radiation and doing lots of parameterizations, consider using the death rate model instead of the instantaneous stop-start to speed up your optimization methods. And with that, I will thank Nicole, who did the majority of this work for her master's thesis, and some collaborators, Karina here in the room and others. And I wanted to say thank you for listening from the mascot of Toronto. And the last thing was just a big thank you to Siv for helping me get to where I am today and for making me laugh every day and reminding me not to take this job or myself too seriously. So thank you.
Okay.